to a new session of a webinar series on data science and statistics, DaSSWeb. Today, we have the pleasure of welcoming Dolores Romero Morales, who is professor at Copenhagen Business School in Denmark. Dolores is especially interested in decision-making and decision-making with optimization. Her areas of expertise include, of course, data science, supply chain optimization, and revenue management. And she has interest in a wide variety of topics, such as explainability, interpretability, fairness, and visualization in data science. She works on large-scale network models for revenue management and environmental issues and robustness in supply chain optimization. Work has appeared in high-ranked journals like European Journal of Operational Research, Management Science, Mathematical Programming, and Operational Research, among others, and she has received various distinctions. She is currently editor-in-chief of TOP and associated editor of Journal of Operational Research Society, Omega, and Informs Journal of Data Science. Furthermore, she currently leads an EU H2020 project, which aims at improving the state of the art in data-driven decision-making through intersectoral and international mobility. Today, Dolores will talk to us about how to learn to be fair in machine learning with mathematical optimization. Dolores, thank you very much for having accepted our invitation to give a talk at DaSSWeb. It's really a pleasure and an honor, and the floor is yours.
Thank you very much, Paula, for the kind introduction, and thank you very much, Eduarda, for the invitation too, and it is the honor for me to be here. So my background is in operations research, so what I'm going to be doing is showing you some operations research models to make more fair decisions with machine learning. First of all, I would like to say that this work is possible thanks to collaborations with PhD students and with colleagues across different countries, and I hope to make clear this every time that I show you one of our papers. So I thought to give you, say, a brief introduction about decision-making with machine learning, the need of transparency and fairness. And then what I will do is to dive into two papers that we have recently worked on. So to show you how we model fairness and the accuracy trade-off. Please stop me if you would like to ask anything, and I understood that at the very end we will also have a Q&A session, but feel free to raise your hand if you would like to check anything. So so for the ones that you know me, I've been working in, say, interpretability for quite a while. We have switched names in the area, interpretability, explainability, transparency. It doesn't matter the name that we choose, but what we would like to do is in a machine learning model to understand what is playing a role. So for quite a while, we have expressed that need for transparency. You can see there that I have a reference from 2014 from colleagues from computer science, but we also have a very recent survey that Cynthia Rudin has written on basically 10 challenges. A couple of them are related to the need of transparency. So I have given to you here a couple of more references in which you can see that actually this transparency has been there much longer, and the 2003 is one management science papers in which colleagues from KU Leuven talk about transparency in credit scoring. So they basically develop models that are, say, gray box, not black box, but gray box, because the regulators basically need to check on what are the key factors playing a role in these models. There is a lot going on in terms of wider regulation. We all have heard about the right to explanation in algorithmic decision making that the European Union came with when the GDPR regulation was introduced. It's not only the EU, it's other public players basically trying to put more regulation into algorithmic decision making. And what we do in our area is, well, we try to put, you know, our contribution it's to try to model this transparency, to try to model surrogates of this transparency, because actually it's very difficult that you find even a definition of what is transparency. But we try to find surrogates and then try to model basically the trade-off between the accuracy of your model and the transparency of that model. So to this aim, there are different approaches, as I say. Some groups, what they have tried to do is to say, well, if I want to impose this, transparency in my model, what I'm going to be doing is using as few features as possible, so construct sparse models. And you can see there quite a few references from different groups, from different timescales, in which they have tried to do to build an sparse model, either directly with a L0 norm or with something that is a surrogate. So, for instance, in our case, we have here a paper on regression, the ordinary least squares regression, in which what we did, it was to put sparsity to a kind of a variable that is called a hierarchical categorical variable, and we try to use as few categories as possible, because then we can give an sparse model. This sparse model is not only important in terms of transparency, but it's also important in terms of robustness, because it avoids to be basically fitting a model to some noise. So what we did, it was to build a mathematical optimization model in which we try to see whether these categories can be merged to an upper level without a dramatic loss of sparsity. And we built the Pareto frontier, and it ended up in our numerical illustrations. We could see that there is basically a gain in sparsity without damaging too much the accuracy. And we have seen this, say, in quite a few applications. People also interpret transparency by talking about prototypes in the data set, so key observations of the data set. And recently we published a paper with one of our PhD students in which we were trying to find these prototypes in cluster analysis. So we were trying to find key observations that would be representative of the clusters, but that would be enough far away, say, from the prototypes from another cluster, so that they would be distinctive. Another way that different groups have tried to enhance the sparsity or in machine learning. The transparency in machine learning is to say, hey, I'm inclined to build a model that is a white box or that is a gray box. And typically, decision trees are considered to be white boxes, and rule-based models are also seen as white boxes. And then what you have seen is a growth in the amount of people trying to build optimal trees or optimal, say, set of rules for classification and regression. In our case, what we have done, we have written recently a review of these optimal tree methodologies, and they are normally based in say discrete structures in which you move an individual to the left or to the right in the tree. So and this is basically not very scalable, because if your training sample is large, then you have a lot of 0-1 decisions to make, and that can be not easy to do. So what we have done is to offer an alternative, which is to say, we move the individuals with a certain probability to the left and to the right, so we don't need anymore to model these with 0-1 decision variables, and that makes our feasible region of our operations research model much easier to handle with, putting more the complexity into the objective function, because we have a highly nonlinear objective function. But this new approach that we have developed is actually quite useful, because it allows us to get interpretability also in a local function. Finally, another way that people have tried to enhance transparency is by building a surrogate of a black box model. So we build a black box model because we think that is more accurate, and then through the information of that black box model, then we try to derive a surrogate that is more interpretable. So some of the colleagues have tried to derive, decision trees from black box models. And actually, recently we have done this together with a PhD student in La Sapienza. What we have done is to say, hey, we have a black box model. For instance, we could have a tree ensemble, or we could have a nonlinear supervector machine. And what we do is to try to identify which are the critical values of a feature. So say that you have this Boston data set, which is about houses, and that you have different features. And for these features, imagine that they are normalized, so they are between 0 and 1, and you try to detect what are the critical features. So if you see something very, very, very dark in this heat map, that is a threshold that comes very often in our methodology. And if you see something very, very light in yellow, it means that the result doesn't come very often in our methodology. And our methodology is based on counterfactual analysis. So what we did, it was for each observation, we found a counterfactual. And a counterfactual is say an observation that is in the other class and as close as possible to your observation. And then every time that we cross the border, we make a note, and that's a possible threshold. And then we do this for all the points in the data set that are correctly classified. And then we have lots of thresholds, and the ones that come very often, they will be in dark, and the ones that come very light, very few times, they will be in a light color. And with this information, what we did, it was to build a decision tree on these thresholds that they are very often coming, to us. And then what we do is to offer this as a, say, white box surrogate, and we could empirically show that if you have enough of these thresholds, your accuracy is not damaged. Yes, Emmanuel?
Thank you, Dolores. But can you please explain for the right-hand side diagram, what is the vertical axis? I understand the horizontal axis.
If we would count here how many rows we have horizontally,
Yes.
it's the number of
It's
features.
frequency. So you count each feature by one.
Yeah, and
there's
then
no weight on the features.
Yeah, exactly.
Okay, thank you.
And then if a threshold comes very often, then we give it. So this is relatively the importance of the threshold. So from 0 to 1. So in relative terms. So we are counting how often we are crossing the border, and then we end up with crossing the border more in some areas than in other areas. And actually, this picture is very simplified because on the left-hand side, I seem to have a very nice boundary, but actually the boundary could be the boundary of a random forest, and then it will be a little bit more messy, but I just was presenting something very neat for the illustration. But actually we did this for gradient boosting, and that would be, you know, a messier picture than this one.
May I ask another question?
Yes.
Sorry, so you count the maximum value across all these features which have of a certain threshold. So
every time I have a threshold, I make a
Yes.
note of that threshold, and then I count how many times that threshold came with the contrafactor. So say Emmanuel, you're a point in the data set. Paula is a point in the data set. Eduarda is a point in the data set.
Yes.
So for each of these points, I'm calculating a contrafactual, and then I see that there is a threshold that for Emmanuel, for Paula, and for Eduarda is repeated. So that would be a darker color. That may be a threshold that only appears for me. And with those thresholds, what we do is to discretize what it was a continuous variable.
Yes.
And then what is known in the literature is that I could basically work better with discretized data, and that's what I do. I discretize the data with these thresholds, but of course the discretization would be finer if I take all the thresholds, and the discretization will be a little bit higher level if I take only the very, very dark ones. And that's what I have. That's the trade-off that I have. How many of these thresholds I take? If I take very few, then I have something that it's an easier to understand tree. If I take more thresholds, then I will need to have a deeper tree, and this is what we play with in terms of interpretability.
So it's data-driven discretization, not
exactly, and yeah, exactly, and that's what people call supervised discretization. But what we also claim is that our supervision is done with an optimization model, which is the counterfactual model. Because in that counterfactual model, we have basically an objective function that allows us to put a zero norm in the number of features that we use and so on. So we have, we have a parameterized methodology that allows us to basically get this right-hand side picture. Thank you very much for the question.
Thank you.
So, and I wanted to actually tell you, because this is a way that is coming out also quite a bit in terms of transparency, is these counterfactual explanations that I was showing in the previous one. You could see me using the counterfactual explanations to understand what are critical values. So these counterfactual explanations are getting more and more traction in our area. So there is a little bit of different basically groups working on them. So Martin and Provost's 2014 paper in Bakshi 2017 paper. So very, very different groups. So information technology, computer science groups. But anyway, there are many more papers coming out, and the rest of these citations are basically reviews that are coming out in different journals. So what you are trying to do is you are trying to offer an individual that got, say, undesired prediction. So say that you are trying to get a loan and then you got a rejection, and this contrafactual explanation gives you, say, information of an individual that is close to you that got the loan. And this individual can be one from the data set, or this individual can be a made up. And then the optimization problem is about minimizing, say, the dissimilarity to that individual. Yeah, I'm not going to talk about this today, but it's a different way of enhancing the transparency. So here the individual and the prediction model are given. So this is what we call a POSOC way of enhancing interpretability. So somebody got a rejection, and then what you are trying to find is an alternative. So your loan has been denied. So if your salary would have been a little bit higher, 33K, and if you had, say, less account open at the bank, then you would have got the loan. And in our group, what we are doing is trying to do counterfactual analysis, but say for a group of individuals, so that we can learn how the model works. It's not only about the individual, but it's also about the stakeholder who is using this model to understand what is important in the model and to impose desirable constraints. So my claim, and I always try to put them together, is that if you try to be fair, and I will show you in a second what we could understand by fair. If you try to be fair, first you have to understand the model, and that's why I have put a few slides about transparency of models. So now we go and talk about fairness, and it's basically a necessity nowadays to check on the fairness of our model, because some decisions are being automatized and some decisions are basically affecting individuals through the algorithms that we use. And I put here a couple of examples. So such as the social benefits in the Netherlands. So that was a big case. It's a country that I tend to follow quite well because I did my PhD there, and so my family law is from there. So this was a big case in the Netherlands in which certain groups basically were affected by social a social benefit scandal in which they were told that they had to return loads of money, and actually that didn't need to be the case. And so some lawyers figure out that this was basically an unfair way of making decisions in which say sensitive group was being contacted to return this amount of money. But I'm also putting there other cases like the A levels in the UK when the COVID year in 2020, exams couldn't be taken for the A levels, and again the algorithm that was used to basically find surrogate grades was discriminating certain kids, certain schools. Yeah, so the literature here is growing again at a very, very high pace. I'm putting there a couple of people, actually, some of them from the OR arena, that they are also trying to contribute to this literature. And just to be very clear, if I have a sensitive group and I have detected what is the attribute of that sensitive group, is not enough to basically remove that sensitive attribute from the data set. So if I think about a data set that I will show later on about income, gender, it's the income it's clearly lower for females than for males in that data set. You remove that gender information, but it's indirectly in other features, as this audience will be very well aware of these correlations. Then, you know, even if you eliminate that sensitive attribute, it will be hidden in others. So that's something more has to be done. So what people tend to do in terms of enhancing fairness, actually, you can have pages and pages of fairness criteria. I'm just going to be very short today, but some of the reviews that I have there list many different criteria. And if you try to optimize for one fairness criteria, you will basically go against another fairness criteria. So I just would like you to be aware of this. So, so sometimes what some of the papers are trying to say is, I have a sensitive group, say I was talking about females, so I try to make sure that I control the accuracy in the whole data set, but I also control the accuracy in the sensitive group. So sometimes people call this sensitive supervised learning. Yeah. Cost, in the sense that you try to penalize, is one way of doing things. You try to penalize more the error in the sensitive group that you would do in the non-sensitive group. Another way to apply, say, fairness criteria, it would be to say that yeah, the two accuracies are very similar. So this could be sometimes a bit problematic, because then maybe what you're trying to do is trying to have a bad accuracy in both groups. But anyway, that's not what we try to do. So we will try to control in both cases, but because otherwise, you, as I said, you will be equally bad, and that will be a feasible solution. Another way of making sure that you are fair is that the predictions, so say that I belong to the sensitive group because I'm a woman. So then what we try to do is that the prediction I will get, it will be similar to the prediction that somebody else will get with similar features to me, but from the other gender. And I will try to show today actually a methodology that is doing something close to this. Yeah. So I was trying to be very schematic, but we can fill up easily 3 slides with different fairness criteria. Okay, so I mentioned that I brought today with me 2 papers so that I can give you more details and give you a little bit of the flavor of the models that we need to use in operations research. And in the conclusions, I will show you that we are working in other methodologies. The first methodology is going to be, say, a random forest, although any tree assemble will be fine with me, so gradient boosting or anything else. Yep, but for the sake of the presentation today, I will call it a random forest. So, I mean, random forests are, we decided to study them because people tend to like them. They give you this variable importance that people see as a surrogate of how key that feature is. We all know that this variable importance has its own issues, but it's a good, yeah, it's a good starting point to basically evaluate what should be the key features in your model. So I would like to do today, I would like to choose for you a random forest that is using few features, because yeah, that will be good for the user to focus in as few as possible features. But of course, as usual, I care about accuracy, but I'm not calling this accuracy. I'm calling this fair accuracy, because I would like to make sure that my accuracy it's paying attention to the sensitive group. So in a second, I will give you a precise definition of what fair accuracy is in this paper. Yeah. So let me do a couple of steps so that I get to my final objective in the model that I'm going to optimize. So I told you that I would like as high as possible fair accuracy, and I would like as high as possible sparsity, because that would be good for my transparency. Well, yeah, for my own sakeness, I'm going to work with error instead of accuracy, but it's totally equivalent. And instead of sparsity, yeah, I'm going to measure how many features I'm using. So I'm going to work with the complexity of the model. Yeah. And look at what I'm going to be doing. So I'm in charge of the random forest. So I'm not going to use any subroutine or any package that you like. I'm myself, I'm going to be in charge of the trees. So what do? We generate lots of trees, and in our case, they are stump trees. But our methodology is equally working with, say, deeper trees. Yeah. But so what is a stump tree? Is the smallest that you can construct. So I give you a feature, I give you a dressel, and that's one stump tree. I give you another feature, I give you another dressel, and that's another stump tree, and I have T of them. Yeah. How can I get those T trees? Well, if you do a random forest in which you limit the depth of the trees to 1, that will be one way of doing it. But if you have knowledge yourself that you can generate then yourself, and if you want a very simple way of doing this, you just take the features, you just take, say, the percentiles, so and then you have very natural dressel for these features. Yeah. So I told you that I want to be sparse. So my model, my optimization model is going to control the sparsity, and it's going to control the sparsity with a yes or no variable. So I'm going to remove some of these trees because these variables were not used. Yeah. So if I have, say, a variable type of job in my adult data set, then if I don't use that type of variable, then that tree is going to be eliminated. And you see this in a light gray. Yeah. And then from the remaining ones, what my optimization model is going to do is going to reweight the trees, because the weights that I had to start with, yeah, they may not be good anymore because I have eliminated some of the trees. So I'm going to weight each of the trees. So obviously that's another decision that I need to make. And then I will I will make decisions with those weights and those trees. So then yeah, I have an individual, and then the individual will run through each of the trees, and then the individual will end up in a leaf node, and then I will see what is the class of that leaf node, and then I will start summing up these weights from the nodes in which I was in. And then I will have a score for the positive class, and I will have a score for the negative class. And then the majority, for instance, rule would say to me that I go to the class 1. So nothing very special here, because this is the way we normally work in random forest. The only thing is that I now control the weights myself, and I control the features myself. So that will allow me to model fairness, and that will allow me to model accuracy. Okay, so what is my data to start with? I don't want to bother and go line by line, but I hope you realize that I have a training sample. I hope you realize that I told you that I have the trees myself. Yeah, so I have all the information at the trees, which features they are using and how they are predicting. Yeah, so that's data for me. And what is the decision variable? Which are the decision variables that I have? I have the weights that I'm allocating to each of the trees, and the weights are between 0 and 1. They are normalized. And I have the variables that control whether a feature is being used or not. Yeah, so these are the information. Now, the beauty of say the model, and apologies, this is what I see as the beauty is coming. We don't model here, for the sake of scalability, we don't model whether an individual is correctly classified or not in a hard way. We model in a soft way, because if we were to do it in a hard way, again, we will need 0, 1 variables for each of the data points. And we are trying to avoid that, because we know that that's in general not scalable. And we have seen this in many papers in the literature. So we do it in the soft way. So therefore, we need this variable, this chi variable, and this chi variable for some of you, and I know that in my audience, I have experts in the super vector machine. So you are going to appreciate this variable, because it's very similar to the deviation variables that you have in a super vector machine model. So let me show you what we do. If you believe for a second that this chi variable is measuring the error that I'm making in each of the individuals, it's normal that I do average error for all the individuals, and that I do average error for my sensitive individuals, because I told you that I wanted my accuracy to be fair. So I'm giving extra weight, extra alpha weight to the individuals in the sensitive group. Yeah. I told you that I would like to select features. So I have a 0, 1 variable that decides whether a feature is selected or not, and I have a budget. A budget here of how many variables I want. And of course, if I see that a tree is using a variable that has not been chosen, so I'm modeling this with big M constraints. So if I see a tree that is using a variable that I'm not using, so this is equal to 0, then the weight of the tree is equal to 0. So the tree disappears from my tree ensemble. Yeah. And I have a parameter M to control the largest weight that I have. The weights sum up to 1. And look at this. I told you, so this is where I'm modeling, say, in a soft way, whether I'm making an error or not. I told you that I would like to, that I make assignments to a class with these weighted scores. Yeah, so I showed to you here before that I had a 0.9 and I have a 0.10, and I went to the 0.9 because it was the highest. So now I know that this individual belongs to the class KI. So this is data. I know this for a fact. So if I don't want to make a mistake, I should ensure that this score should be the highest. So I want to go to that class because it's the correct class. So I want to ensure that this is the highest. So that's what I do. I make sure that it's higher than for any other K, but in a soft manner. Yeah, and not so hard. I'm not making this say in a hard way, but I allow this error chi I, and this is what I'm trying to minimize, the error that I'm making. So I hope that this sounds a little bit familiar to the soft margin constraint that I have in supervector machines. And here I have the definition of the variables. And the good thing is that, yes, I do have 0, 1 variables, but I have much less than if I would do a hard implementation of the correct classification. This is just to explain this new constraint, but I think that should be clear by now. And what I have is my methodology has a parameter alpha. If I give an alpha equal to 0, then my methodology doesn't care about fairness. And if I have a very high alpha, so the highest that I have here is equal to 1, then I care a lot about the sensitive group. So obviously, if I care a lot about the sensitive group, you see that this line is very close to 0. If I don't care much about the sensitive group, the error in the sensitive group is much higher. And my claim is that we can have, say, a good trade-off. So one of these middle lines has reduced the error that I make in the sensitive group, and you see it does not affect by much the error that I make in the whole population. So I can gain fairness without harming too much, without harming, say, the accuracy that I have in the whole group. And another of the things that I would like to stress is that this sparsity that I'm pursuing, actually, it comes very natural because I don't need to use all the features. You can see over here that these lines get very flat, meaning that I was trying to give a budget, say, of 15 features, but my model is happy to use fewer features, meaning that sparsity, say, comes for free without harming, say, the accuracy. So what I'm going to be doing, I'm aware of the time, but I'm going to show you another methodology that we have recently developed with a master student here in CBS to try to enhance, again, the fairness of another methodology that you know, which is now we are really working with supervector machines, and I'm going to show you how to enhance that fairness. So I hope I can use, say, 7 or 8 more minutes, Paula. So yeah, I think we.
Please go ahead, no problem.
Yeah. Okay. So so what I'm trying to do here is my starting point is a supervector machine, a non-linear supervector machine. So I do have a kernel, and what I'm trying to again to do here is the trade-off between my accuracy and the fairness. This time, the fairness is about looking at the distribution of the predictions in the sensitive group. So we have been talking about gender, but you could also be talking about certain race, yeah, like in the COMPASS data set. So we look at the predictions in a group, and that gives me a distribution, and we look at the predictions in another group, and this gives me another distribution, and I try to make sure that these distributions they resemble each other. So in a second, you will see me talking about distance between distributions. A typical, or say a popular distance is to use this Wasserstein distance that again is very close to operations research, because it has behind it an optimal transport problem, and that's what we are going to do. But we are going to say use that distance on the scores that we get from the supervector machine. So let me go say to the regular SVM. Yeah. So in the regular SVM, what you have is you are given a kernel. And we normally tend to work with a dual formulation. So we are in the dual. So we are trying to say for each individuals, we are going to have these alpha, which are our decision variables. Say we have this constraint in which, you know, yes, the summation of the alphas weighted by the class of the individual. Yes, so this is -1 or +1, the class of the individual. So the summation is basically cancels out. Yeah, these alphas are between 0 and a parameter C, because this is the parameter that allows me to basically put more or less importance on the errors that I make. And this is a, say, we work in the dual because we can solve efficiently this quadratic programming problem that has been basically well studied in the literature. So how do I make decisions with a supervector machine? So with a supervector machine, so once we have solved this problem, we have the alphas. And then what we do is that for an individual, we have the alphas, we have the labels of the individual, as I said, positive or negative label. And then we have basically, say, the kernel of that individual to every individual in the training sample. And once you have calculated this summation, then you have a number. The people who are above a threshold will go and be classified as positive, and the people who are basically below the threshold, they will be classified as negative. So if you don't do anything, it could be that from the sensitive group, I have quite a few people with low scores, and I will illustrate this to you in a couple of slides. And that's what we are trying to prevent. We are trying to prevent that we have too many individuals from the sensitive group in the say, in the low scores, because they will be classified as negative. So that may have an impact on them if the negative class is the one that you don't decide to have. So for instance, like the negative class is being rejected below. Yeah. So that's why what we are going to try to do, and I have tried to put this in a very schematic way, we try to look at the, say, the distribution of the scores. And obviously the distribution of the scores will depend on the alphas. I've shown this to you in the previous slides. So the distribution of the scores for the sensitive group and for the non-sensitive group, I want these two distributions to be very close to each other. So I have put here calligraphic D to tell you that I could have put there any distance. And actually, there are different papers that are put in there different distances, not necessarily for the supervector machine, but for say logistic regression and for other methodology. So what we have done is to say, well, we are going to put there the Wasserstein distance, and the Wasserstein distance is nothing else than as I said, a transportation problem. And I've written here what is the general Wasserstein distance for two discrete empirical distributions. In our case, the U and the hat U would be the scores in the sensitive groups and the score in the non-sensitive groups. So this is what we are doing. We are trying to have the regular supervector machine, but now we are penalizing. So we want the Wasserstein distance to be small, and this is a max. So yeah, we put a minus in front so that it's something that I want to make small. If I have a maximum, I have to take the negative, and I put a tau because I want to control the importance that I give to that fairness. So I hope it's very clear what I'm doing. This is again what I find beautiful in this paper. So is the fact that let me go back one slide because I want to. So this is the Wasserstein distance. So the Wasserstein distance is basically trying to move mass from one distribution to the other distribution. So it's actually matching. It's doing a matching between the observations, and this matching pi is what we call the optimal transport plan. Yeah. So so this is actually an optimization problem by itself. So writing out the whole model, I would need to basically put the pies into the model. I'm not going to do this today. It will take me more slides, but I would like to show you something that it will be very revealing of the optimization methodology that we are doing. Yeah. So remember that there is a pi to be calculated here, and obviously the pi will depend on the alpha. So what happens if I know the pi, so say that I fix for you in advance the pi, then I have a supervector machine. And that's the beauty of this paper. So if I give you the pi, then what you have is a supervector machine in which you have a different kernel. And what is the different kernel? Is the one that you had already. So I'm still measuring the dissimilarity in the way that you were doing it before, but I'm adding something more to that dissimilarity that is to do with, say, the fairness, and it's to do with this, say, matching between individuals from the sensitive group and from the non-sensitive group. So L belongs to the sensitive group, M belongs to the non-sensitive group. So that matching, and also how much the say the kernels will differ in those individuals. So we can prove that actually this is again a kernel. So what we do is an alternating procedure in which I fix the pi, I can get a supervector machine, I get a new alpha. If I get a new alpha, I have a new pi, and then I will start all over again. If I do that, look at what happens. So I hope the picture is big enough. This is the adult data set, which is a data set on income. And I told you that the sensitive group here, we decide to be the female group. And look at the female group. The female group is a red group. And then if you look at the red distribution of the scores, they are more around negative scores, while the non-protected group, which is the remaining of the observation, is more around positive scores. So very clearly, if I would run a supervector machine trying to predict income for future individuals, females are going to basically be more often predicted low income. So I will basically amplify that inequality that I have in the data set. So what we do is by putting a little bit of weight, just a little bit of weight to the fairness, then we can get the two distributions a little bit closer. Apologies, I didn't bring this information. I should have noticed that I didn't put the caption, but from this plot to this plot, we have no loss on accuracy in this data set. I'm not saying that this is a general, is true in general, but in this data set it is not. And what I can tell you is that this is a common thing that we have seen when we try to gain, say, in fairness. And of course, if I give more weight, you will see that at the very end, I will get them very close to each other. I'm not recommending that you do that, because the accuracy that you get here is very damaged, because you are only focusing basically on fairness. So how can I make very fair my model? Take an alpha equal to 0, and then all the scores are equal to 0, and then you are predicting, say, something that is not accurate, but it's the Wasserstein is equal to 0. So I don't recommend that you get to this point, but what I recommend is with a little bit of weight, you are making your model more fair without losing accuracy. So, and I don't want to take more time, but yeah, we are also imposing fairness on optimal trees, on lasso models, on regression, logistic regression, sorry. And I think it's a good idea that we don't amplify the biases that we may find in the data. Yeah, I thank you very much for your attention.
Thank you very much, Dolores. It was very, very interesting and very actual, very, very important.